Hello, folks. So, this semester I am teaching a course, or rather, I'm a TA for a course on paleoecology, which is the application of ecological techniques to the fossil record, usually within the Quaternary period, the last 2.5 million years, in an attempt to reconstruct what ancient ecologies looked like. This is, in fact, the field where I'm doing my PhD in, and so I thought I would provide some supplemental information to my students or for anyone generally interested in how to use the R programming language, which is what I am doing my doctoral dissertation in, can be used for paleoecology. So I am going to assume for this lecture that you already have R and RStudio downloaded and have gotten yourself to something like this already. So this is our R document where we can make edits to our code and run individual lines, and from where we can save our code to be run in the future. This is the console space where we are going to see what code gets run, and if there's any errors, we'll see them over here. And then over here, we have our data. And then in this corner, we'll have our plots and packages and whatever else we might need. So I always lay out my R code the same way each time. I'm going to start with a header in these commented brackets. So the little pound sign creates the commented brackets. And I'll put a title. Sometimes I'll put more advanced titles like, so this is just for my chapter 1 research in my PhD. And see I've got a longer title. Then I always have my install packages next. And you only have to run an install packages command once and it's installed. But I find that if I have to load a new package that I've never used before over the course of my current project, I'll put the install packages command here commented out, and that way I have documentation supporting the fact that I used it and installed it for this project. And that makes it easier when you're going back and trying to write up like a lab report or a paper and you're like, well, what packages did I use? I have to cite them. Oh, it's right here. All right, next comes our libraries. Now, usually I have much more extensive libraries. Here I'm just using some pretty basic libraries. We're gonna lightly explore dplyr and lightly explore ggplot, but you can see on some of my other work, many more libraries end up getting used in this sort of stuff. So again, we run these once, and then each time we need to run the script anew, like each time we launch RStudio, we're gonna run these. Well, I've already run these, but to run them, you just sort of highlight them and come up here and click run. And you can see that it's already all there. Now we're gonna bring our data in next. Now for this project, I'm not gonna use any data, but so I've commented that line out. But the way you do this and the way you set your working directory and all that is come up here to import dataset. In this case, we're going to do it from Excel, and we can browse. And here you can see it. Here's a piece of data that I can use an Excel spreadsheet that will be imported as a data frame. I'm going to cancel that for right now. But this piece of code will be displayed in your console, and I would say just copy and paste it so you can just highlight this line and run it so that you can automatically load whatever data you want. So after that, I tend to just put my main analysis here and separate it from any graphing I need to do. So let's do some very, very basic R stuff. So we'll start with just building some vectors. Vectors are columns of numbers, and they're sort of the base form of data that R deals with. So I've decided to make a collection of 7 numbers, which I've found to be more or less arbitrary. Use the C. C stands for concatenate. I put the commas in between and the parentheses, and that will make your vectors. Now for the x vector, I've decided to include a vector of 1, 2, 3, 4, 5, 6, 7. And instead of typing those all out individually, I do 1:7, and that will create that vector. So let's just go through here and rerun these. Cool. So let's do some useful statistics on them. We can take the mean of each of them. So the mean is 4. Mean of y, 9.7. And let's take some standard deviation. So we use the command st, take the standard deviation of y, we get a standard deviation of 6.1. Often we're interested in R in using data frames, which are how we store matrices or three-dimensional arrays of numbers for those kinds of uses. So we can use this data.frame command of x and y to make a data frame, and we're going to call it capital D. So we can run that. And when we do that, we come over here to D, click on it, and you can see that our data frame D is presented, and we can look at it, and sometimes it's useful to reference those. So let's see just how linear this is. So one thing we can do is we can evaluate linearity by just doing a simple linear regression model using y is predicted by x given data d, and then we'll use this summary command to pull up our information. When we run this, you can see that there is a statistically significant relationship between x and y, so it's a linear, generally linear relationship. And we have this r² value of 0.67. So what that means is that as x increases, we are also getting an increase in y. So let's take a look at graphing that. So you can graph using the plot function, which is native to R. And you can see we have a graph with this data. Now there are ways to customize our plot function. However, the much more common standard way of doing it is to use the ggplot2 library, which we loaded earlier. ggplot, this is the initial x and y. Geom point means that I want it in points. I want a scatter plot of points. Theme classic means I want a white background. And then these are our labels. Run that. That should give us that. So you can see that we have a higher degree, I think, of control over what we get in this circumstance. Some of those people will ultimately tend to prefer ggplot as their development of R improves. And we can also add that linear method here with the geom smooth, and we should get a best fit line and some errors. So we do that, we see that this line has come down a little bit because we've got these errors, but generally we see this best fit line, this 66% linearity. And we do see that there are some things that are outliers, potential outliers. So let's go and run a little more code that will tell us if, maybe help us see if these are in fact outliers. So let us use one of the functions in the dplyr package with a mutate function that adds a new column. And it's going to add us the column of z-score. So z-score is the difference from the mean divided by the standard deviation. It's the number of standard deviations away from the mean that a particular value is. And so if you have, a really extreme z-score, that's a pretty good indicator that one of your data points is an outlier. So we run that, and we come back over here to D. You can see that a lot of them are pretty close in. This 3, that is 1.1, and then 20, that's 1.6. So that's a lot, but it's not outlandish for being an outlier. So we can come back then to our ggplot, and I've just sort of copied this identically. What I've done is I've added a color and size that will help us look at that more closely. So when I run this one here is popping as being an outlier, and this one here is too. But none of them are unreasonable outliers. You had maybe 40 in here in this data. That would be an extreme outlier. So I think that'll be all for now. I'm sure when I have some more time, we'll come back and we'll do some more. The one thing I do want to say is I want to save this, so I'll do File, Save, and I think I'll save this just to my Year 2 folder and create a file just for this at a later date. So save. I guess I have to name it. So let's call this Paleo Collect 1. All right. So we've saved it, and we can come back to it and use it later. All right, that's it for this time, folks. Have a nice day.